Hi everyone, thank you so much for joining us today for a guest speaker session. We have with us Harsh Trivedi today. Harsh is a final year PhD student at Stony Brook University. He is broadly interested in development of reliable, explainable AI system and their rigorous evaluation. Specifically, his research spans in the domain of AI agents, multi-step reasoning, AI safety, and efficient NLP. Previously, he had interned at Allen Institute and was a visiting researcher at New York University. His recent work, AppWorld, received the Best Resource Paper Award at ACL 24. Today, we will be talking about the same paper, AppWorld. Thank you so much, Harsh, for your time, and I'll pass it over to you.
Awesome. Cool. Thanks, Ahmed, for the introduction, and thank you everyone for joining this presentation. Today, I'm super excited to talk about our work, AppWorld, reliable evaluation of interactive agents in a world of apps and people. This is a joint work with many of my amazing collaborators from Stony Brook University, Allen Institute for AI, and Salem University. The talk roughly has four sections, and I'll stop after each of them to take questions. But if you have any question, any clarification question, anytime during the talk, feel free to ask them. Um, all right, so I want to start this talk by painting a broad vision behind this project before diving into this specific work. Many of us use AI agents that act on our behalf in the digital world. For example, assistants like Siri, Alexa, and Google Assistant are agents that can already do simple tasks on our behalf, like setting an alarm, checking weather, and making a call. In the future, I believe these agents will become far more capable. They will be used for doing more complex tasks and will be adopted and integrated even more broadly into our society. Everyone will have their own personalized AI agent through which they will interface with the digital world and to some extent, even the physical world. These agents will coordinate with each other and even with humans to achieve complex collaborative tasks. There will also be agents that act on behalf of organizations like hospitals, banks, and so on. And their actions will deal with real world resources that will have real world consequences like transferring money, sending medical records, and so on. So, as we move towards such a world, it is important to ensure that these agents become more capable, reliable, and trustworthy. The long-term goal of this project is to build a simulated world which acts as a foundation for reliable evaluation and development of such agents embedded into our society. AppWorld is a step towards this long-term goal, and that is what I will talk about next. AppWorld is a simulated world and a benchmark that focuses on the setting where AI agents individually and autonomously complete day-to-day tasks on behalf of people on their app accounts. It includes tasks such as returning an Amazon order and buying a replacement, sending owed money to friends on Venmo, and canceling meeting reminders based on coworkers' emails. Agents can operate apps to do such tasks broadly in two ways: by interacting with the browser and mobile user interface, or by calling APIs exposed by these apps. At the end of this talk, I'll briefly discuss our ongoing work on agents interacting with the user interface. But for most of this talk, I'll focus on agents calling APIs. Although calling such APIs is the main ingredient, just that is not enough for complex tasks. Here, the calls to the APIs have to be made by writing rich code in an interactive manner. Let me explain it by showing how an ideal agent could tackle an example task. That is, play my shortest Spotify playlist with enough songs for today's workout. My workout plan is in simple note. To solve this task, first the agent has to find the user's workout duration. For this, it gets the user's simple note credentials, logs in, searches for the workout related notes, all via writing a code snippet, making appropriate API calls to the simple note app. Notice here that the output of the first API is going as an input to the second API. Still, both of these calls can be made into the same code snippet without knowing the value of the token variable. This is possible if the agent knows the output schema or type information of the first API and input schema or type information of the second API. However, what to do next depends on the free-form text present in the notes variable, and so the agent has to print it. The agent finds a note with free-form text indicating day-wise workout durations. So it prints the current day to find today's duration. Notice here that the agent printed today's day because it found a note with day-wise workouts. But the user's notes could have been organized in many different ways, each of which would have required a different code snippet. For example, if there was a note with month-wise workouts, the agent would have printed the current month instead. This means that here the second code snippet had to be written interactively based on the first code snippet's output. All right. So now at this point, the agent knows today is Tuesday. So it infers a 45-minute workout and searches for the shortest playlist with enough songs for that duration. To do this, agent has to loop over the playlists, find total duration for each, and filter and select them accordingly. Doing this involves writing rich code with various programming constructs like loops, conditionals, arithmetic, and so on. So in summary, we saw that a seemingly simple day-to-day task can be quite complex, and it had two key requirements. It required environment interaction to write the next code snippet, and the code itself was rich with various programming constructs. So the key question we ask in this work is, how can we develop and benchmark such rich and interactive coding agents for complex digital tasks in a rigorous and reproducible manner? To do this, as it will become clear later, we need three ingredients: a realistic and reproducible environment of API operable apps for agents to interact with, a benchmark of complex tasks requiring API calls with rich and interactive coding, and a robust programmatic evaluation framework for checking agents' code completion. There are many existing tool use benchmarks like Cohere, Toolbench, API Bank, and many more, but they do not support these requirements. Their tasks are simple with only a linear sequence of 1 to 4 API calls. They have a small number of API implementations or use unstable APIs. And they use human or LLM judgment or reference-based evaluation, which is not robust for complex tasks that have many solutions. So to bridge this gap, we introduce AppWorld, a world of apps and people. It constitutes a new environment, a challenging benchmark, and a robust evaluation framework. Next, I will talk about these three components, starting with the environment. So we want to create an environment of API operable apps like Amazon, Gmail, Venmo, and so on. We want this environment to also support reproducible experiments, complex tasks, and robust evaluation. Reproducible experiments require resetting the start environment to identical state whenever we want to run an agent on a task. Complex tasks require tailoring the start environment specifically for that task to be compatible and challenging. And lastly, robust evaluation requires accessing the final environment state, as complex tasks can be solved in many ways. So to satisfy these requirements, we need full control on the state of the environment, which for an app-based environment is defined by the databases underlying each of these apps. So in other words, we need full control on the app databases. Now this rules out the option to build this environment from real apps implemented by the companies, because their proprietary app databases are fully controllable only by them and not by us. So we instead implement simulated versions of these apps in our own backend of APIs and databases, which provides us or anyone with full control on the app databases. Simulated apps also provide other benefits over real apps. The real apps require real resources. For example, when payment needs real money, whereas in our simulated apps, it is just a database entry indicating who paid whom what. Simulated apps are fast, always up, and have no rate limits, which is not the case for real apps. But all of these benefits are not enough. We also need richness, realism, and complexity of real apps. And to do this, we have spent huge amount of effort in making these apps to be super rich and high fidelity in nature, meaning that they have closely similar features and behavior to real apps. Our implementation spans over 60,000 lines of code, have 457 APIs with detailed documentation, and 100 plus database tables. Our apps have fine-grained and detailed functionalities. For example, the Gmail app won't be just send and read emails. As it is in real life, emails will be organized in threads within your inbox and outbox. You can reply and forward individual emails from them to different contacts. You can schedule them for a future time. You can manage your drafts, attachments, labels, to search over them, and a whole bunch of other things. Actions or API calls in these apps also lead to realistic in-app and cross-app consequences. For example, when you place an Amazon order, your cart is cleared, the product inventory is updated, your payment card is debited, and it shows up in your past orders with tracking information. And you also get an email confirmation with a receipt as an attachment. These apps also have authentication and privacy features like login, sign up, forget and reset passwords, and so on. And they prevent access to others' private information as well. And these APIs always provide informative error messages and never blanket errors like internal server error. For example, if the agent tries to send money to someone via a payment card that does not have enough balance, the API will respond with a message saying so. This allows the agent to learn by interaction. These apps also have been extremely rigorously unit tested. We have over 1,700 plus unit tests spanning over 34,000 lines of code and providing a test code coverage of 98%. We want the agents to be able to explore this environment arbitrarily without the environment breaking or behaving unexpectedly. This rigorous testing gives us high degree of confidence that we have such a reliable environment. And as discussed before, these apps also provide full programmatic control over the database state. And we use this control to populate these app databases with rich and realistic data. As I will show later, this data will help us build complex tasks. In particular, we create a simulated world of 100 plus people. In this world, each person has their own personal accounts on all apps. They also have a home and work address for online delivery and payment cards for monetary transactions. This allows for personal tasks like buy a t-shirt for my home delivery using my Visa card. These people are also related to each other in this world. We have various relationships like parent, friend, sibling, partner, and so on. This allows for relational tasks like email my partner that I'm running late. These apps are also populated with personal and interpersonal digital activities of people which are consistent with their relationships. For example, on the top, you see an employee sending an email to his manager asking for a leave approval. On the left, you see two roommates chatting about the apartment bill payment over the phone, and so on. These activities are populated spanning 2+ years of time, which allows for temporal tasks like delete my emails from last year. Overall, the resulting database has 100 plus tables, 350K plus rows, and 750 plus columns. Note that this data is generated procedurally, by sampling from human in the loop LLM generated data as opposed to by people simulated via LLM agents. And the resulting world of apps and people, which we call base world, provides us with a rich and realistic foundation to build the complex tasks on top of. And I will show how we use it later in the benchmark section. So next I'll talk about the benchmark, but I can also pause here to see if there are any questions.
I have a question. So, can you talk a little bit more about the data generation process? Like,
Yeah.
what were the steps and how was human intelligence?
Yeah. So basically, the question is how we create this data, right? I think one clarification I want to make here is that uh, the data that we generate over here, it's generated procedurally, and it is not generated via LLM agents. For example, we are not trying to simulate each of these people via an LLM agent and then letting them loose in the world and generate the data. Instead, we are doing this construction procedurally. And there are like over 100 plus tables, and different tables and different combinations of tables require different slightly different approach. So here what I will do is I'll just give one example of how a Gmail emails tables could be populated, and that would give you a sense of how the data generation is done. So um, so imagine we want to populate Gmail email tables via this group of people who are like roommates, coworkers, friends, and so on. So the first thing that we do is we generate a large number of templates for conversations that different people could have with each others. For example, what kind of conversations roommates could have with each others, or coworkers could have with each others, friends could have with each others, and so on. And then we use those templates and instantiate them for different people at different times, and then use it to populate the Gmail emails table. And how this templates are written. So there is like a we do some of writing. We also use a little bit of chat gpt here and there to able to maybe expand the list a bit. But in the end, it's all of that is kind of reviewed by us to make sure it is the data is sensible and um, agrees with the format and the requirements that we have. Does that give you a sense of how data generation is done?
Yeah, makes sense. Thanks.
Cool. Thanks. Okay, so uh, next I'll talk about the benchmark and specifically how we construct the AppWorld benchmark, and specifically how we design complex tasks. So for this, we start by writing day-to-day scenarios, which naturally require rich and interactive coding. Here, a scenario is an ungrounded blueprint for the task. For example, buy the product that my related person suggested someday. From this scenario, we can create multiple tasks like buy the shirt that my roommate suggested today, buy the desk my coworker suggested yesterday, and so on. Now, remember that we want, let's look at the first task. Now, remember, we want the agent to follow this instruction by taking actions in the environment. So just the instruction is not enough to define a task. We also need a world state, which constitutes the database state and current time within the world. And we also need a supervisor, who is the person in the world on whose behalf the agent is supposed to operate the apps. For the task to be solvable, we need the instruction, the world state, and the supervisor to be compatible with each other's, meaning all conditions required to follow the instruction are satisfied in the world state for the supervisor. For example, in this task, today is 11th February, and the supervisor is Alice. Here, as per the database, Alice's roommate has suggested her to buy a Nike shirt today via a phone conversation that you can see on the left. This Nike shirt is available now on Amazon, and Alice has enough funds in at least one of her payment cards to make the purchase. These conditions make the task to be solvable. However, mere solvability is not enough. We also want the tasks to require thorough reasoning to solve. For this, we include distractors, hurdles, and task variations. Here, including distractors means making it so that bypassing any reasoning step will likely mislead the agent to the wrong path. For example, here, Alice will have shirt suggestions not only from today, but also from days before. So if the agent ignores the word today, it will likely fail to identify the correct shirt to order. Similarly, there will also be other distractors as well. So if the agent ignores the word shirt or roommate, it will also similarly get distracted. Next, we also include hurdles, which requires agents to do realistic failure adaptation. Excuse me, it requires agents to do realistic failure handling and adaptation. For example, here one of Alice's payment cards has no money in it. So the agent has to realize to try another card when that one fails. And lastly, we also include task variations, which requires agents to reliably solve tasks under slightly different or contrastive conditions. For example, remember we created this task by grounding the scenario. Similarly, we can create a different task by differently grounding the same scenario. Notice that here two tasks have different current times, supervisor, placeholder values, and the database states. Note here that these variations are carefully designed to also catch shortcuts that distractors cannot. For example, on the left, the key relevant suggestion has come via a phone message, and on the right, it has come via an email. So the agent needs to check both email and phone for suggestions to succeed on both the tasks. All right, so now we know how what we want from the tasks. Let's see how to ground the scenarios into tasks so that they satisfy the required initial conditions. And to do this, we use the base world that we discussed earlier. Remember that this world already has a rich, fully populated app databases, including people and their activities. This world provides a reusable foundation that can be used across scenarios. However, it does not satisfy task-specific requirements. So we will need to adapt the base world for each task, as I will show in a bit. To ground a scenario, we need two things. We need to select the placeholder values, like shirt for a product, roommate for a related person, and so on. We also need to satisfy the required initial conditions. Some of these conditions can be satisfied by doing a search in the app databases of the base world. For example, to find a compatible supervisor, we can find a person in the world who has roommates. But for other conditions, search is not enough. Instead, we need to edit the app databases. For example, the base world doesn't have a phone conversation about the shared suggestion between Alice and her roommate. So we need to create one by building, excuse me, so we need to create one by editing app database. Now note that this is a simplified picture. In practice, there are many conditions, often interdependent with each others. So for having the flexibility, we do all of this programmatically by writing the task setup code for each and every scenario. All right, so now that we have the tasks, we want to programmatically guarantee that they are indeed solvable. And so for this, for each task, we write solution code and evaluation tests, and then programmatically verify that running this solution uh, passes all evaluation tests. Here, I want to emphasize that each task scenario poses unique requirements. So all code has to be written individually for every scenario. It has taken over 5+ hours for each scenario and over 40,000 lines of code overall. To maintain high quality, all scenarios and code have been developed by us. It is not crowdsourced, and they have been reviewed multiple times by multiple people. And here are some more sample tasks from AppWorld. The first task is I'm going on a camping trip with my siblings. I email them a checklist of the needed items, check who committed to bring what, then order the remaining items on Amazon. The second is I booked a few hotel rooms today for my upcoming trip. How much did I spend in total from my Visa card based on the email confirmations? And the last is I bought a few shoes on Amazon this week, but only the medium size one fits me well. Initiate a return for the rest, preferring UPS as the deliverer if it is available. To solve these tasks, the agent is given an instruction, the API documentation to understand how to use these APIs, and an interactive coding shell with an API client. For example, we have this shell. Agent can log into Spotify, explore API documentation interactively, or obtain supervisor's personal information. By default, we provide an IPython-based shell, but one can really use any programming language with any HTTP client of their choice. And based on our written solutions, we find that AppWorld tasks are quite challenging. They require 1 to 4 apps, 5 to 25 unique APIs, 10 to 200 API calls, and 20 to 130 lines of code. All of this is assuming our perfect knowledge of APIs. In practice, agents require many more API calls and lines of code as they learn by interaction and exploration. Overall, we have 750 tasks built from 250 scenarios. Remember that each task scenario can have multiple apps as shown on the left. From across all the 9 apps which are available, we hold out 2 apps, Amazon and Gmail. All tasks involving any of these two held out apps are moved into the test challenge split, and the remaining are randomly divided in the train, dev, and test normal splits. Notice here that we have 2 test sets, test normal and test challenge. The test challenge is our main test set, in part as it forces learning to use APIs for held out apps by reading and understanding the API documentation. Additionally, test challenge also has inherently harder tasks as well. All right, so next I'll talk about the evaluation, but again, I can pause here for questions.
I have one more question. So, are these tasks like uh, so these are like some of the tasks that you have like manually defined. So, are these tasks like expandable or like generalizable? So, for example, if there is any task that you have not like manually defined, but will it generalize to any other tools that are not, for example, Zoho Mail or Microsoft Mail, which was not like initially. So will it expand on all the other tools as well?
Yeah, so correct me if I'm wrong, but I think the question is that would models, if you show them tools or APIs for some of the apps, would they also generalize to tasks which are defined on unseen apps? Uh,
Yeah, yeah.
right? Okay,
Yeah.
so yeah, that's a great question, and that's exactly why we have this kind of two test sets. We have this test normal and test challenge, and the main goal of test challenge was essentially that we want to test that if agents can generalize to new apps which have like completely new documentation and APIs and so on. So if you notice, what we do is we select these two apps, Amazon and Gmail, and then whatever tasks are available, excuse me, whatever tasks involve any of these two held out apps are moved into the test challenge split, and then the remaining are divided randomly. So the train set over here is going to be used for demonstrations and example selection, or if you want to do training, things like that, right? But if you notice the way we have done the splits, the Amazon and Gmail app would always be held out uh, uh, if you're using train set for demonstrations and things like that. So Amazon and Gmail are just not seen, are just do not exist in the train dev sets, right? So if you want to test like how much agents are able to, um, uh, work on like unseen apps with new documentation, then test challenge is the spread for it. But if you just want to see if agents are able to do the task, even if the apps or documentation might be seen, then you would use the test normal split. In addition, it's not just that there is the only difference between test normal and test challenge. It just also turns out that test challenge is like inherently harder. But the main reason for creating this two splits was essentially having this kind of unseen apps to be able to test that. Does that answer your question?
Yeah, makes sense. Thanks.
Oh, thanks. All right. So next, I'll talk about the evaluation. So now that we have the tasks, we need a way to robustly and programmatically evaluate agents. Agents can solve such tasks in many ways. For example, they can download Amazon receipt um, from the for example, they can download an Amazon receipt from its API or its order email confirmation. Both are completely valid approaches, even though they are taking like completely different routes. So therefore, comparison to a reference solution cannot be used for evaluation. And therefore, AppWorld uses a state and execution based approach. In particular, the agents start with the initial database state associated with the task. The agent makes series of code executions and we get the final database state. We compute the difference between these database states to obtain cumulative changes that the agent has made to the tables, rows, and columns. And then we programmatically check whether they include all desired and no undesired changes. We do these checks roughly in a hierarchical fashion, going from tables to rows to columns. For example, for our task about buying a shirt on Amazon, we first check that only a small list of tables has changed, namely Amazon orders, inventory, and so on. This simple assertion captures vastly many ways an agent could have caused undesired changes or collateral damages. For example, if the agent initiates an Amazon order return when it was asked to buy something, the Amazon returns tables will change and this test will fail. We then check that only €1 has been added to the orders table and that this order has only the expected Nike shirt and nothing else. And so the takeaway of doing all of this is that regardless of what path the agent takes in making the desired changes, it will pass. And regardless of what undesired change the agent makes, it will fail. Now, using these assertions, we define two evaluation metrics. Task goal completion, which checks that all tests in a task pass, and scenario goal completion, which checks that all tests for all three tasks in a scenario pass. Next, let's discuss the experiments. For experiments, we benchmark agents built from open and closed LLMs by carefully adapting four strong few-shot prompting methods. First is React, which I will talk about in a bit. Others include plan and execute, that adds a planning stage before React. Function calling, that leverages native parallel function calling ability of language models. And full code reflection, that attempts to generate full code for the task. And if needed, retries based on reflecting on the error stack trace. In interest of time, I will only explain the overall best performing method, which is React. So React first generates a natural language thought about what it wants to do, and then follows it up with a code snippet to do that. Depending on whether the code execution succeeded, the environment prints an output or an error stack trace, based on which the agent decides what to do next, and the sequence repeats. So now let's see the results. Here the x-axis shows different open and closed LMs, and y-axis shows different, and the y-axis shows the task completion score on the test normal spread. Here the score refers to the maximum score achieved by that LLM across all four few-shot prompting methods. We see that GPT-4o struggles getting only under 50 points, even in this easiest setting, and other LLMs are much farther behind. Next, let's see the robustness of these agents. Remember that our scenario goal completion captures whether agents can reliably complete all three tasks of a scenario, which are variations of each other's. We see that going from task goal completion to scenario goal completion, all scores significantly drop. For example, GPT-4o drops by 17 points, going from 49 points to 32 points. This shows that indeed agents do not complete these tasks reliably. Furthermore, when we go from test normal to test challenge, which is our main test set, all scores significantly drop further. For example, GPT-4o only gets 13 points in scenario goal completion. And when we break down the GPT-4o numbers into individual prompting methods, we find the React agent works the best and others lag further behind. Now we have developed AppWorld tasks in 3 levels of difficulties, which allows us to analyze how the agent scores change with increasing task difficulty. Here, the histogram shows the distribution of tasks as per the difficulty levels. And the lines show the task goal completion scores for different prompting methods. We see that the best scores drop from close to 55 to close to 20, going from level 1 to level 3, indicating that agents struggle much more on harder subsets of AppWorld. And we see similar trend for other indicators of difficulty as well, like number of APIs and lines of code as per our written solutions. And finally, based on manual error analysis, we find that agents make a variety of mistakes. They make incorrect assumptions about the environment without looking into or interacting with the environment. For example, in the Amazon task, the agent assumes his suggestion has come via a phone message and doesn't check emails, and as a result fails. They also struggle to adapt based on errors properly. For example, on placing the order when the environment says the payment card doesn't have enough balance, it gives up instead of trying another card. They also forget state because of long trajectory. For example, the React trajectories are often more than 35 steps or 35 code executions long. And they also use APIs incorrectly, ignore crucial pieces of instruction, make various kinds of coding and common sense errors. So yeah, so that's all I had to talk about this project. Next, I'll talk about the future work. But before that, I can also see if there is any more questions here. Okay, so next I'll talk about some ongoing and future work. So as we have seen, solving Apple tasks require many skills like writing code as per documentation, interacting with the environment, dealing with long-range dependencies, and so on. Apple provides a rich and flexible development environment to explore research methods for learning these skills. These skills are also applicable to solving complex tasks in other domains as well, like science and software engineering, but they are harder to acquire in the available environments. And to acquire the skills and make progress on Apple, there are many research directions one can pursue, like learning to self-play on Apple environment, training language models for interactive coding with API calls, learning a high-level skill or function library on top of our APIs, and exploring planning-based, search-based, and memory-augmented approaches. And soon, all of this research will also be doable in a multimodal version of AppWorld. So far, I have talked about agents calling APIs, but sometimes apps don't expose public APIs. So agents should also be able to interact with the browser and mobile user interface directly. In this work, we implemented many API operable apps via our backend of APIs and databases, which can be operated with an API or HTTP client. In the follow-up work, we have also created browser and mobile user interfaces for all of these apps. The UI is closely similar to real apps, and it is backed by the same backend of APIs and databases. So now agents can operate over all modalities to solve Apple tasks. And since Apple tasks and evaluations are database state-based and process agnostic, they can be reused as is. All right, so now let me take a step back from what we proposed in this work and revisit this broad vision that we started with to lay out some more future work. We envisioned a future where AI agents will get deeply embedded into our society, taking various roles and responsibilities. In such a society, agents will have to collaborate with other agents and humans to complete complex tasks. They will have to work in messy real-world environment that require dealing with failures. They will have to be resourceful, making sure they are not wasting your time, money, and other resources. And because real-world resources are involved, they will have to be robust to inevitable security attacks. And after all, agents will deal with people, so they will have to be socially intelligent and fit into our social norms and expectations. Apple provides a fully programmatically controllable and extensible society of people and their digital activities. This foundation can be used to develop and evaluate agents in all of these directions. And if you're interested in any of them, please reach out and I would be happy to chat further. So, in summary, we have introduced AppWorld, which was born out of a significant engineering effort by our team, writing over 100,000 lines of code. We have developed a rich and fully controllable app environment with simulated activities of people. On top of it, we developed a benchmark of complex tasks with robust programmatic evaluation framework and showed that best LLMs struggle on it. And we discussed many future works that AppWorld can support for building better agents and new agent benchmarks. So please check out appworld.dev for Task and API Explorer, Playground, Leaderboard, agent trajectories, and a lot more. We have made AppWorld to be very easy to use and fast. So you can just pip install it and start building and testing your agents. And if you have an agent, the code on the left is all you need to run and evaluate it on AppWorld. That's all I have, and I'm happy to take questions.
Great work. Thank you for the presentation. I have a question. So, have you tried the evaluation of medical agents as well, or how we can create the medical data and use that for evaluation?
Um, Excuse me. Can you say it again? You mean medical tasks?
Yeah, medical tasks, and there are some medical LLM agents as well.
Yeah. Um, the tasks that we have over here do not have anything particular about like medical domain, so we have not tried it. But um, yeah, I mean the core is like pretty straightforward to use. So if someone wants, they can definitely try it out. But because the tasks are not specific to that domain, we did not try that.
Great, thanks.
Cool.
If we don't have any other question, we can conclude the session.
Right, cool. Thanks everyone for joining this presentation again, and yeah, thanks for the
Thank you so much.
questions and
Thank
comments. Yeah,
you.
cool.